You are strapped into a seat the size of a bathtub, hurtling toward a planet at 20,000 kilometers per hour, and the last message from Earth arrived 11 minutes ago. It said, "Good luck. There is nothing after that." Not because Mission Control has nothing to say. They have everything to say. But because the physics of light and distance mean that by the time their next transmission reaches you, whatever is going to happen will already be over. You will be dead, or you won't. The universe has not decided to wait for human commentary. The date is sometime in the 2030s. You are one of 4 crew members aboard the Artemis Mars Transit Vehicle, a craft that weighs, fully loaded, approximately 41 metric tons, and that is about to attempt something only robotic spacecraft have ever done: survive entry into the Martian atmosphere. Your heat shield is 4.7 meters across. The corridor of atmosphere you need to thread is less than half a degree wide. Too steep, and you burn. Too shallow, and you skip off the top of the atmosphere like a stone off water, back into space, with no second chance. The 7 minutes that follow will be the most dangerous continuous interval in the history of human spaceflight. And here's the thing nobody tells you before you leave. We still don't fully know if it's survivable. From a distance, Mars is patient. That's the word that keeps appearing in the journals, in the mission planning documents, in the quiet conversations between astrobiologists who have spent careers staring at its photographs. Patient. It sits at an average distance of 225 million kilometers from Earth. Though that distance breathes, pulling closer to 54 million at opposition and retreating to 401 million at its farthest. And in every image it looks almost reasonable. A rust-colored sphere, rocky plains, the tallest volcano in the solar system, Olympus Mons, rising 21 kilometers above the surface, and a canyon system, Valles Marineris, that would swallow the continental United States whole. In high-resolution imagery from the Mars Reconnaissance Orbiter, the surface looks almost inviting. There are slopes that resemble frozen lava flows in Iceland. There are dried riverbeds, real ones, carved by real water, billions of years ago, that look like photographs taken from an aircraft over the American Southwest. The light is pale and amber. The sky, in certain conditions, is a faint lilac blue near the horizon at sunset. It looks, in other words, like a place a human being could stand. That impression will kill you if you let it. Because here's what the photographs don't transmit. The atmospheric pressure at the Martian surface averages 636 pascals. Earth's sea level pressure is 101,325 pascals. You step outside without a suit on Mars, and the moisture on the surface of your eyes begins to evaporate. The dissolved gases in your blood begin to expand. This condition has a clinical name, embolism, and it is not a quick death. The atmospheric composition is 95.3% carbon dioxide. The mean surface temperature is negative 60 degrees Celsius, but the diurnal swing is violent enough that a single Martian day can move from negative 73 to positive 20 degrees at the equator. In the polar regions in winter, it reaches negative 125, and something is wrong before you even get there. The something wrong is not on the surface. It's in the gap between the surface and you. Entry, descent, and landing on Mars has a nickname in the aerospace community. They call it the 7 minutes of terror. The phrase was coined by engineers at NASA's Jet Propulsion Laboratory during the Curiosity rover mission in 2012, and it spread because it was accurate, not poetic, not marketing, accurate. The Curiosity entry, with a vehicle roughly the size of a car, required a heat shield capable of absorbing temperatures exceeding 2,100 degrees Celsius. The entry sequence was so complex, so intricately choreographed, that the JPL team described it as having 76 pyrotechnic events that all needed to fire in sequence without a single failure. That was for a 900-kilogram rover. You are asking the same atmosphere to slow down a crewed vehicle that is more than 45 times heavier. The Martian atmosphere is the cruelest possible design for entry. It is thick enough to generate catastrophic aerodynamic heating, the kind that turns the air in front of your heat shield into a plasma sheath hot enough to melt steel. But it is not thick enough to complete the job of slowing you down. On Earth, parachutes can do significant deceleration work because the atmosphere is dense. On Mars, by the time you've slowed enough for parachutes to deploy, you're still moving at several hundred meters per second, and you're already dangerously close to the ground. The atmosphere of Mars is simultaneously too much and too little. It is, by a kind of terrible coincidence, exactly the wrong density for human-scale vehicles. This is not a new problem. This is a problem engineers have known about since the 1990s, and every proposed solution has carried a new set of failure modes. But here's the part nobody talks about. The entry corridor, that half-degree wedge of atmosphere you have to hit, is not a fixed target. Mars has weather. The Martian atmosphere expands and contracts based on dust storm activity, and dust storms on Mars are not like dust storms on Earth. They are planetary scale events that can envelop the entire planet for months at a time. In 2018, a global dust storm killed the Opportunity rover, which had been operating for 15 years, by blocking enough sunlight to starve its solar panels. For a crewed entry vehicle, a dust storm doesn't just obscure visibility, it physically changes the density of the upper atmosphere, which changes your deceleration profile, which shifts the corridor, which means your pre-calculated entry angle is no longer correct, by fractions of a degree that will decide whether you live. The heat is the first layer. The plasma that forms around your heat shield during peak heating reaches temperatures between 1,600 and 2,100 degrees Celsius, depending on entry angle and vehicle geometry. For context, the melting point of steel is 1,370 degrees. The tiles on the Space Shuttle's thermal protection system, made of a silica-based material called HRSI, were designed to withstand 1,260 degrees. They failed at 1,650. The Columbia disaster in 2003 was caused by a breach in the leading edge of the left wing, measuring approximately 15 to 25 centimeters, roughly the size of a dinner plate, that allowed superheated plasma at roughly 1,400 degrees to penetrate the vehicle's interior. From breach to structural breakup, 46 seconds. Your heat shield on the Mars entry vehicle is larger, made from newer materials, carbon-carbon composite reinforced with ceramic fiber, tested in arc jet facilities that simulate entry conditions by electrically heating gas streams to plasma temperatures. The material performs well in controlled settings. The Orion capsule, during its first uncrewed test flight in 2014, successfully endured 2,200-degree temperatures for a period of several minutes. But there is a difference between a test and a 41-metric-ton crewed vehicle with a non-uniform mass distribution entering a dynamic atmosphere at an angle that must be correct to within 0.3 degrees. And this is where the data stops making sense. NASA's Mars Climate Orbiter was lost in 1999 due to a navigation error caused by a failure to convert between metric and imperial units. The spacecraft entered the Martian atmosphere at the wrong angle and was destroyed. The error was 0.93 degrees. The cost was $327 million, 10 months of transit, and every piece of scientific data the mission was designed to collect. For a navigation team working with the full resources of NASA, communicating in real time, that error still happened. Your entry is autonomous. There is no real-time communication. The decisions are made by software running on processors built to survive the radiation environment of deep space, which means they are not the fastest processors available. Radiation hardening requires architectural compromises, and those processors are executing a sequence of maneuvers that cannot be paused, reviewed, or corrected from Earth. If something unexpected happens, the software decides. You are a passenger. The invisible killer is not the heat. Heat is visible, measurable, anticipated. The invisible killer is what the heat does to your communications. During peak heating, the plasma sheath surrounding your vehicle is not just hot. It is electrically conductive. Radio waves cannot penetrate it. For approximately 4 minutes, centered on peak heating, you are in a communication blackout with every relay satellite, every ground station, every crewed asset in the solar system. This is known. It has been modeled. It has been experienced by every Apollo crew returning from the moon and by every robotic entry at Mars. What has not been fully characterized is the interaction between that plasma blackout and the autonomous navigation system running your entry. The plasma doesn't just block radio, it generates electromagnetic interference across a broad spectrum. The sensors your navigation system uses to orient itself, accelerometers, gyroscopes, star trackers, are shielded, but shielding has limits. In 2020, a study published in the journal Acta Astronautica by a team at the University of Queensland modeled plasma-induced sensor noise during Mars entry and found that, under certain atmospheric density conditions, accelerometer readings could be contaminated by electromagnetic noise at a level sufficient to introduce guidance errors of up to 2 kilometers in the final landing position. 2 kilometers on a planetary surface doesn't sound catastrophic, but you are not landing in an open field. Every proposed human landing site on Mars, the Jezero crater region, Isidis Planitia, the ridgeline south of Hellas Basin, was chosen partly for surface smoothness. The margin for landing error is measured in hundreds of meters. 2 kilometers puts you on terrain that was never surveyed for rocks larger than 50 centimeters, which is the threshold above which your landing system's legs can fail on contact, which tips the vehicle, which is unrecoverable. Scientists have a name for what happens if you tip on landing on Mars. They call it an irrecoverable dynamic event. They don't fully understand all the ways it can happen. There is a third layer, and it does not involve heat or navigation or electromagnetic interference. It involves you, not your suit, not your equipment, You. The human body has never undergone a Mars entry. Apollo crews returning from the Moon experienced approximately 6.5 g of deceleration during re-entry. Mars entry for a large crewed vehicle is currently estimated to peak between 8 and 12 g, depending on the final vehicle design and entry parameters, and will sustain that loading for a longer continuous period than any crewed re-entry in history. And you have been in microgravity for 7 months. The physiological consequences of extended microgravity on the cardiovascular system are well documented. Fluid shifts toward the upper body, reducing the heart's workload in ways that cause it to structurally remodel. The cardiac muscle thins. Astronauts returning to Earth after 6 months aboard the International Space Station routinely experience orthostatic intolerance, meaning they cannot stand upright without their blood pressure dropping to the point of near fainting. For most returning ISS crew members, this resolves over days to weeks, but they are returning to Earth's gravity, not entering a sustained high-G deceleration corridor over a period of several minutes, in a vehicle undergoing violent aerodynamic perturbations, requiring them to remain conscious and capable of emergency manual override if the autonomous systems fail. A 2022 paper in NPJ Microgravity by researchers at the European Space Agency examined cardiovascular responses to simulated re-entry conditions following microgravity exposure. Their finding was careful in its language, but alarming in its implication. Cardiac output under high G loading following extended microgravity may be insufficient to maintain cerebral perfusion in some individuals. Insufficient cerebral perfusion has a simpler translation. You black out. In the most dangerous 7 minutes of your life, when the system most needs a human override, you may be unconscious. But that's not even the most disturbing finding. The most disturbing finding comes from a subfield of atmospheric science that most people working on crewed Mars missions spend very little time discussing. Mars does not have a global magnetic field. Earth's magnetic field is generated by convection currents in our liquid iron outer core, and it extends tens of thousands of kilometers into space, deflecting the solar wind, a continuous stream of charged particles emitted by the sun, around the planet. This is why Earth has an atmosphere after 4.5 billion years. The magnetic field is the shield that prevents the solar wind from stripping the atmosphere away. Mars lost its global magnetic field approximately 4 billion years ago. The leading theory, developed through analysis of magnetic anomalies in the Martian crust mapped by Mars Global Surveyor, is that the Martian core cooled and solidified, ending the dynamo. Without the field, the solar wind began stripping the Martian atmosphere at a rate that, over geological time, reduced a once thicker atmosphere to its current remnant state. Mars still has no global magnetic field, and you are entering that atmosphere during solar maximum. The Sun's activity follows an approximately 11-year cycle. At solar maximum, coronal mass ejections, massive eruptions of plasma from the solar surface, occur more frequently and with greater intensity. A coronal mass ejection that reaches Mars can compress the induced magnetosphere that partially protects the planet and temporarily strip additional atmosphere from the upper layers. During a significant CME event at Mars, radiation levels on the surface can spike by a factor of 50 over background. Background being already approximately 100 times higher than what you'd experience on Earth's surface. But the atmosphere itself is the relevant variable. A significant CME in the days before your entry subtly alters the upper atmospheric density profile. Not dramatically, not enough to be classified as a crisis, enough potentially to shift your entry corridor by a fraction of a degree. The Mars Atmosphere and Volatile Evolution Mission, MAVEN, has been monitoring this process since 2014. The data shows that atmospheric mass loss events during CMEs are real, measurable, and unpredictable in their precise timing. MAVEN's principal investigator, Bruce Jakosky, at the University of Colorado Boulder, described the stripping events as episodic and variable, not constant, not modelable with sufficient precision to build into an entry corridor calculation more than 48 hours in advance. The universe, in other words, is still writing the atmosphere you have to fly through. And here is the anomaly. Here is the thing that sits in the data and has no clean explanation. MAVEN and Mars Reconnaissance Orbiter have both recorded events in the Martian upper atmosphere that don't correspond to any known solar or geological trigger. Localized density spikes, transient aurora-like emissions in regions where the crustal magnetic fields shouldn't be strong enough to generate them. The word used in the relevant papers, published in Geophysical Research Letters in 2019 and 2021, is anomalous, not a cover-up word. A precise scientific word, meaning we measured it, we cannot explain it, and we are not yet confident enough to build a model around it. Your entry corridor passes through the upper atmosphere. The altitude at which your autonomous navigation system begins making active corrections is the altitude at which these anomalies have been recorded. No one has told you this will kill you. No one has told you it won't. And then there is a moment, perhaps it comes at the end of the plasma blackout, when the first faint signal reaches the relay orbiter and the orbiter bounces it back to Earth, and Mission Control in Houston takes a breath they have been holding for 7 minutes. There is a moment when the dread and the data and the heat and the uncertainty resolve, not into safety, but into something else, into the fact that you went, that 4 human beings looked at the corridor and the plasma and the physics and the blackout and the anomalous readings in the upper atmosphere and the 41 metric ton vehicle that had never done this before, and got in. Carl Sagan wrote in Pale Blue Dot that every human being who ever lived, every king and peasant and saint and sinner, every creator and destroyer of civilizations, lived out their lives on a mote of dust suspended in a sunbeam. He meant it as a call to humility. But there is another way to read it, that the mote of dust produced something that looked outward, that the thing the universe made out of carbon and water and 4 billion years of catastrophe looked up, got uncomfortable, and decided to go somewhere harder. Mars from orbit is still beautiful, even knowing what it is, even with the physics and the CMEs and the crushing atmosphere and the anomalous readings in the data. It is genuinely, unambiguously beautiful. The polar ice caps, the shadow of Olympus Mons at dawn, stretching 600 kilometers across the plains, the thin line of atmosphere at the limb, glowing a faint electric blue in the moments before sunrise, an atmosphere so thin it would kill you, glowing like something that wants to be seen. The terror does not go away. It becomes the point. Because the question was never whether Mars was safe. It was never whether the corridor was wide enough, or the heat shield was thick enough, or the autonomous navigation was good enough. Those are engineering questions, and engineering questions have engineering answers. And the engineering teams at JPL and ESA and JAXA and every contractor who has touched this mission have spent decades on those answers. The question underneath all of it, the question that the 7 minutes actually poses, is older than aerospace. It is older than science. It is, how much of the unknown are you willing to enter? You land, or you don't. The universe is not dramatic about it. The data either continues transmitting or it doesn't. The relay satellites either pick up your beacon or they spend the next 11 minutes sending a signal into silence. But here is what is true regardless of what happens in that corridor. We are a species that built a craft, loaded it with 4 of our own, pointed it at a rust-colored world 225 million kilometers away, in conditions we do not fully understand, with physics we have not completely characterized, through an atmosphere that the universe is still actively writing, and launched it anyway. Not because we were certain, because certainty was never the offer. The universe does not owe us a survivable corridor. It does not owe us a stable atmosphere or a predictable magnetic field or a safe landing site or enough time to learn what those anomalous readings mean. It has been indifferent to us for 13.8 billion years, and it will be indifferent for whatever comes after. We went anyway. We went because something in the carbon and the water and the 4 billion years of catastrophe that made us is constitutionally incapable of looking at a question and leaving it unanswered. 7 minutes. Every civilization we will ever be is decided in 7 minutes. And the most extraordinary thing about those 7 minutes is not whether they end in survival. It's that we found a way to be inside them at all.